So now we're going to look at molecular orbital theory, or MO theory, and this is more complicated. As a result, we're going to look at even simpler molecules, as homonuclear diatomics. And so valence bond theory is great for figuring out geometry and explaining what we see when we look at molecules, but there are some properties such as magnetism that don't really get fully explained by the valence bond theory, and so that's why we have to look at molecular orbital theory. We always try to explain the properties based on Lewis structure alone because that's the simplest model, but sometimes it's not enough and we have to go further into more complicated ideas. So we've talked about atomic orbitals. That's the 1s and 2s and 2p. Those are our atomic orbitals. Now we're talking about molecular orbitals. And these molecular orbitals are thought to belong to the entire molecule. They don't belong to a particular atom. They belong to the whole molecule. And so we say they're delocalized. And what that means is it's kind of community property. So kind of like when we were doing Lewis structures, we said, well, all I'm really worried about is how many valence electrons I'm bringing in. I don't really care who brought them in or where they're assigned. We're just saying, well, they belong to the molecule now. The same thing when we're looking at molecular orbitals. These are associated with the entire molecule, not with a particular atom on the molecule. But one thing we will see is that the number of atomic orbitals going in must equal the number of molecular orbitals coming out. And remember, these are just models to help us better understand and predict the behavior of these molecules. Just a little refresher here on the meaning of diamagnetic. So diamagnetic means that all of the electrons are paired. While it does mean that we have an even number, the word diamagnetic means all the electrons are paired, because just because we have an even number of electrons does not guarantee that something is going to be diamagnetic. We can have an even number and be paramagnetic because we have an unpaired electron. So we're going to look at oxygen as an example. And so if I look at valence bond theory and look at the properties, look at the Lewis structure valence bond model of O2, what I expect is that all the electrons are paired, and therefore it would not be attracted to a magnet. But when I actually look at oxygen in a magnet, I see something very different. So what you're seeing here is a magnet, a very powerful magnet, a very strong magnet. In pouring out of this is not actually water, but that's actually liquid oxygen, which we need to handle a little carefully because liquid oxygen's flame is a fuel for combustion. Liquid oxygen is pretty explosive because we're concentrating all of those molecules close together. So we do handle this carefully. But what you see here is actually liquid oxygen being suspended between these two poles of the magnet. Now you also see what looks like steam or smoke. That's just the condensation of the water because everything is very cold, so we're getting some water condensing from the air when we do this. But the liquid oxygen is actually being suspended between those, and that indicates that it's actually paramagnetic, that it has an unpaired electron, something we wouldn't expect from looking at the Lewis structure of the model. So what we're going to look at is think about this a little bit differently. Instead of talking about just these atomic orbitals, when we go to molecular orbitals, so these on the left represent our atomic orbitals that are going in. What's in the middle here are our molecular orbitals. So when I'm looking at hydrogen, again, simple molecule, what I see is that I have two 1s orbitals, atomic orbitals, that combine to form two molecular orbitals. And we see our sigma, so some things are staying the same from valence bond, and we say the 1s because it's the sigma orbital formed from the 1s. But we also have this, what we call a sigma star 1s, and so this is known as an antibonding orbital. The sigma 1s is known as a bonding orbital. It's lower in energy, it's more stable. So adding electrons to a bonding orbital improves the stability of a molecule. Adding electrons to an antibonding orbital is going to decrease the stability of that molecule. So an antibonding orbital has a higher energy and is less stable. So we can actually look at this for more than just looking at H2 or F2. So we're looking at an example here to keep things simpler but introduce a new idea is if I look at H minus ion, what I see is if it's H minus, that means it's gained an electron because it has a negative charge. Hydrogen here still has one electron. When I form the H2 minus, so it's got a negative one charge overall, I've got to have three electrons because I had three electrons in my atomic orbitals. I've got to have three electrons in my molecular orbitals. I put the first two electrons here in the lower bonding orbital, the sigma 1s. There are no degenerate orbitals, so I can put them both in the same orbital. We'd follow the same rules for filling molecular orbitals that we do for atomic orbitals. But I have two here. I still have one more electron to go, and so I'm going to put it up here in the sigma star 1s. So this causes the molecule to be destabilized in the formation of this. So we'd say, well, that H minus is less stable, or H2 minus, excuse me, is less stable than the H2 molecule, because we have an electron in that anti-bonding orbital. So now let's look and see what happens with the helium molecule, so He2. Now that wasn't on one of our molecules that we had to learn as diatomics, because it actually doesn't exist, because when we look at this, what we see is that there are two electrons in the bonding orbital and two electrons in the anti-bonding orbital. So the presence of these two electrons destabilizes the ones that are in the bonding. So as a result, this molecule actually doesn't form. And so it's not a stable molecule because there's just as much anti-bonding as there is bonding. Now we can go on to the helium-2 with a plus charge ion. We go back to having 3 electrons, so we see 2 bonding and 1 anti-bonding, so comparable to the H2 minus anion that we saw. So we have some destabilizing effect from this anti-bonding electron, but we also have 2 electrons in a bonding orbital. So this can form, although it's not incredibly stable.